Hello everyone, welcome to Rubber Industry NewsHour. This is a Technobiz weekly online program for a global rubber industry. In this NewsHour, we have technical talks, panel discussions, and also leadership conversations, research developments, and a number of things in the rubber industry, focusing on the rubber industry. So I welcome you all for this Rubber Industry NewsHour. We are on the episode number 33. In this episode, we are focusing on advances in rubber testing instrumentation. This full episode is all about these advances in rubber instrumentation. In this session, we have 5 speakers from the various rubber testing instrument suppliers. And also we have an expert on the rubber technology who will be also joining as a panel as part of the discussion session. So let's before we get into more details about it, let me introduce to you all of you about the Technobiz. Technobiz is based in Thailand, established in 2005. It is recognized as an international resource center for the rubber and many polymer industries. Just give you some idea about some of the activities of what we do. We organize the exhibitions. This is a GRTE. It's on the 29th to 31st March in Bangkok. And we have a show Middle East Rubber Expo, which is focused on the Middle East region, scheduled on the 21st to 22nd November next year in Sharjah. You can find more details about this event if you like to book a booth or you would like to visit these shows at expo.technobiz.org. As part of this both events, we also have the rubber research and patents. We focus a lot in rubber research, as you know, so because the research is an important component of the industry development. So in all our shows, we invite researchers to put the posters on the research developments. So in this, both shows have the rubber research and patents. We also add this time as patents as well. We publish books. We have a number of books for the rubber industry. You can check our store.technobiz.org. Along with the rubber industry books, we also have a magazine, Rubber and Tire Digest magazine. It is jointly published by the Technobiz and Rubber World. We do have an online training program for the rubber industry. You can check more details about these online training programs at knowhow-webinars.com. In this one, you have short training programs, you have master classes, and also we offer the diploma programs as well. We have we are introducing the next year executive diploma 360 degrees. Focusing on the rubber industry, technology and management. This is 3-month-long diploma program. In this one, this is purely focused on a non-tire industry. This is not suitable for the tire industry people, but is a non-tire industry professionals. They must have a little experience to join this diploma program. We have 2 batches next year. We welcome you to check the details at the knowhow-webinars.com. And this is today's session episode of Rubber Industry NewsHour. We have started in January and we are currently on 33rd episode. Every week we cover various issues that is relevant to the industry. Sometimes you have technical topics, sometimes you have a market outlook, sometimes you have the leadership conversation. We're trying to cover a broad range of issues for the rubber industry and every week. And this is available. It's free to join. Currently, there are 3,000 subscribers from the different parts of the world join. Some of them join the live session. Many of them join the record session later on. Okay. We also offer the digital marketing for the rubber technology. If somebody is interested to take our service, we are specialized in the digital marketing for the rubber products as well as rubber technologies. We can check more details on our website as well. Okay, and just give you some additional information on upcoming events. Okay. See, this is an upcoming event in India. This is International Rubber Conference, IRC 2022, organized by the Indian Rubber Institute during the 24 to 26 November in Bangalore. And you can check more details about this conference at the irc2022.com. Okay. And as I repeatedly mentioned about our exhibitions by Technobiz, GRTE next year, 2023 in March, and Middle East Rubber Expo, and also the Rubber Research and Patents. I welcome you all to participate in these industry events. Useful to all of you. Every exhibition is useful. You get updated, and you have opportunity to network and explore the business opportunities. Let's come to today's episode, Rubber Industry News Hour. Our focus is on the advances in rubber testing instrumentation. In this one, we have 5 experts specialized in the rubber testing instrument. They are from the rubber testing instruments manufacturing companies. They will be presenting on the latest developments from their company. And this is our schedule. These are the topics which will be presented in this episode. I'm expecting this is going to be a long session today, as we have 5 different speakers and different topics, and each person probably around 20 to 25 minutes length of the presentation. And first, all the speakers will make a presentations. After that, the discussion session is there after presentation. So you can ask the questions, on any of the topics. When you want to ask questions, you can type your question box. Make sure you attention to the speaker name and type your questions. We will put this questions in the in the Q&A session, or I call it a discussion session. It's not. You can also ask any general issues about rubber testing. All the speakers are very well experienced and knowledgeable. I'm sure that they will give you some guidelines and suggestions as well. Feel free to post your questions in the question box. Okay. So let's welcome. Presentation is by Dr. Raj Ganesh from the TA Instruments. He'll be speaking on the advanced thermal characterization techniques of rubber materials. Raj has more than 17 years experience in the field of polymeric material characterization techniques and their processing techniques. Currently, he's working as the application support manager for the last 10 plus years with the TA Instrument, a division of the Waters. He's based in India. His expertise is in the study of the structure property relationship of the polymer materials, processing relevant material characterization, material property correlation with the processing behaviors. So let's welcome Raj to give a presentation on the advanced thermal characterization techniques of rubber materials.
Hello everyone. I'm inviting everyone for our rubber industry tech talk. Today, I'm going to talk about advanced thermal characterization technique of rubber materials. The main focus of this technical talk is more about, making you all to understand about the advanced thermal characterization techniques which are available for rubber material characterizations. So we all know how important the thermal characterization techniques for rubber materials and rubber polymeric materials, but at the same time, there are various advanced and unique testing options available today with those standard equipment, which really help us to do advanced characterization, which give us much more detailed understanding about the rubber materials. So before getting into today's topic, let me quickly give an overview of TA Instrument, who we are, what we make. So if you see that today, TA Instruments, we are basically rooted from a DuPont, which is one of the world-known chemical company founded in 1960s by a group of thermal analysis specialists. They started a special techniques which are very much important for polymeric material characterization. And way back in 1990s, as the demand for the thermal analysis became very popular, and there's more and more requirement for equipments, the company people, the same group of people who was dealing with the thermal analysis, got separated and founded a new company called TA Instruments. And then 1996, Waters Corporation has taken over TA Instruments, and today we are very much part of Waters Corporation. Waters focuses, as you know, they are mainly into HPLC mass specs. TA is mainly into material characterization, especially thermal, rheology, microcalorimetries. Our headquarters is in US. What you are seeing in this campus is our major headquarters, which are located in Newcastle, Delaware State, US. And if you see that we have almost 1,000 employees, and 50% of these employees are directly customer-facing activities, and 13% are involved in R&D. That's where the development of new instrumentation, new measurement techniques are developed. And coming to manufacturing, we have totally 5 manufacturing sites across the world, 4 in US and 1 in Germany. Coming to direct sales and service, we have operation almost 26 countries covering 4 continents, including North America, Europe, Asia, as well as Brazil. Each countries we have a technical sales, application, training support, and training service engineers. So we provide a complete support for our customer, starting from the pre-sales and even after sales. When it comes to application development, training, we are there to support. So what do we make? As you know, TA Instruments, we are having 4 product verticals. One of our major strength is thermal analysis, where we have products like DSC, TGA, STT, DMA, GMA. And coming to rheology and rubber rheology, we have range of equipments which are used for understanding about the rheological properties of both polymer, pharmaceuticals, personal care products, as well as rubber. And third group is mainly for microcalorimetry, where we have a range of products like nano DSC, isothermal titration calorimeter, thermal activity monitors. So these microcalorimetry products are very much mainly for the life science industries, where people who are working on, proteins, ligands, those kind of things. And then 4th product groups are about thermophysical properties. Again, here we have got various instruments, such as dilatometer, thermal conductivity, diffusivity. These instruments are mainly used to understand the physical properties, thermophysical properties such as thermal expansion, shrinkage, thermal conductivity, diffusivity. With that series of product, we are actually touching every aspect of material. You can name anything. It could be a polymer, thermoplastic, pharmaceuticals, thermoset, inks or coatings, rubber, elastomers. We are there. We have a solution for that. Okay, we have our instruments. And most of our customers are using our equipments mainly for having a better understanding about the molecular structure of your particular materials. And that's what most of our customers are using our kind of equipment. And today also what we are going to focus is more about thermal analysis, where I'm going to show you how our instruments are going to help you to have a better characterization about rubber and rubber polymeric materials. Let's get back to the topics of today's about thermal analysis. If it comes to the typical properties which are measured by thermal analysis, one is the weight. So we subject the sample to basically to the temperature, change in temperature, and then we will be seeing how the weight of a sample is going to change. That is we call as thermogravimetric analysis. Another aspect is about the heat flow. So when you change the samples, when you change the temperature of your sample, how the heat flow is changing. So that is we made it by measuring the heat flow. And that is the 2 techniques today we are going to focus. One is the weight, how the weight, that is by performing analysis on the thermogravimetric analysis. Another aspect is a heat flow. So that give you more of information about the thermal transition of the particular polymeric material by using differential scanning calorimetry, or we call it DSC techniques. There are other aspect is length, that is we call it thermal expansion, and modulus, which is by dynamic mechanical analysis, and viscosity, that you can do it by rheological. We have previous tech talks. You can refer those things like how DMA analysis and rheology is going to be helpful in that aspect. So as I said, today we are going to focus more on the weight and heat flow part. So let's start with the TGA, that is what is thermogravimetric analysis. So in thermogravimetric analysis, the main aspect that we are going to measure is change in weight of your sample, or change, it could be of loss or it could be of gain, and against the function of temperature or time under the control atmosphere. So basically the thermogravimetric analysis, or TGA, is going to measure the sample weight changes with respect to temperature or time and a controlled atmosphere. So what are the common use of these equipments? Mainly as far as rubber is concerned, you can perform a composition of the material. Suppose, as all of us know, rubber is a multi-component systems. So we have multiple components that if you have a better understanding about the composition of the particular rubber compound, you can make use of a TGA techniques, and that gives the information about the composition of the particular rubber compound. And also it be a very helpful tool to understand the how much of filler, it could be of inorganic filler, how much of filler is there, or if in case of a pipe, fiber reinforced plastic, how much of fiber content is present. That information also TGA can give. Another major aspect is carbon content. As all of us know in rubber industry, carbon black is a very important aspect to improve its mechanical performance, and one has to clearly understand how much of carbon black is present. It could be of a quality control aspect, like if you want to maintain a consistent mixing quality, you can do it. Or if in case of doing something of a benchmark compound or a defective compound, you want to do a comparative studies where you want to understand the carbon black content. And then comes the predict the thermal stability aspect. So this is about the raw polymer. So one has to understand what is the usage temperature of a particular rubber polymer. For that also, TJ would be the good tool to understand the thermal stability. And the third aspect is to characterize a material due to sorption, desorption, or volatile decomposition, oxidation reduction. Suppose in case you are dealing with some sort of a hygroscopic polymeric material which has a tendency to absorb moisture, obviously the moisture which is present in the polymer can affect your performance. So the TJ is the techniques that can clearly quantify how much of moisture present in. In case of an unreactive monomer which is present as a solvent, you can also use a TG as a techniques to quantify how much of solvent content inside the samples. So altogether, TG is the fantastic tool to have a clear understanding about the material composition and how much of filler content into that. So what is critical as far as TJ instrumentation is concerned? The previous slides, what I showed to you is the TA instrument discovery series TGA. So when it comes to any instrumentation, before you purchase any TGA equipment, there are a couple of key aspects that you need to see. One is the furnace. The furnace is the one which controls the heating rate. Furnace is the place where you control the heating rate as well as temperature. You maintain a particular temperature, and then you can also see the atmospheric control. So the furnace is one of the very important aspects. And then comes change in measured temperature that is being measured by basically a thermocouple. And the third, of course, is the balance. Here, the balance is the heart of the system, any TGA, because that's the one which is going to measure the change in weight, actually. So these are the three major criteria. So when before any selection of TGA, you need to see how the furnace is going to control, the heating temperature and the temperature and thermocouples, how it is accurately measure the temperature. So you need to see how much of temperature accuracy and resolution, and then comes the balance performance. Let's talk about more about the key application what TGAs can do. As I said at the beginning, I explained to you the major application is about thermal stability of the material. That is the one of the key aspects, and that is something in terms of predicting the lifetime of your product. So suppose you have the polymeric material, a rubber polymer. How are we going to predict what will be the lifetime of the particular polymer? That thermal aspect, because many applications the material can be subject to thermal and mechanical loading condition in a real world condition. But here the TJ can give you the information about, if respect to temperature, how stable it's going to be your material. Another third aspect is oxidative stability of material. The polymer can be exposed to condition at elevated temperature where there is a higher chances oxygen can attack the polymeric material, and there could be a chance of degradation. So TGA can help you to evaluate that aspect also. And comes to third is the composition of multi-component system. And the same things, this will actually, what we do is, as the polymeric materials, rubber polymers consist of many components. As you know, it consists of, volatile, high volatile component, and then we have the plasticizer, and then we have those polymeric component, and then filler, oils, all those things are mixed together. As we heat the sample, samples start going to evaluate one by one. And that also will be coupled with the evolved gas analysis techniques. In this case, we couple the TGA with the either FTAR or mass spec, and that also give the information further that what type of evolved gas is coming out. This will also give a clear understanding about what type of decomposition byproduct which is evolving from the sample, and many times it also helps us to identify the polymers. Okay, so if you want to have a better understanding about what is coming out of sample, you can make use of TGA with the evolved gas analysis. Okay, and then as I told you, the TGA, we have the option to change the atmosphere. Most often studies would be performed at nitrogen atmosphere, but sometimes you can also do in a reactive atmosphere, and then you can see how the material is going to decompose in particular atmospheric condition. Apart from that, we have moisture and volatile content of the material, estimation of lifetime of the product, and also we can understand the decomposition kinetics of the material. So these are some of the key application, and here I'm going to highlight some of the TGA application in a tire rubber. For example, here you can see this is a typical standard TGA thermogram where you can see we have taken an 11 mg of tire compound and analyzed in the ramping mode. So we are taking a few mg of sample. Generally, it will take 10 to 20 mg of samples and put it at a crucible, TGA crucible. It could be made up of either platinum or ceramic, and then we heat it up the ramp temperature of 20 degrees centigrade per minute up to 600 degree under inert atmosphere, where in this case it's nitrogen as the inert gas. So what we see observe is, you can see on the x-axis is basically a temperature, and y-axis we can see on the left hand side is a weight percentage, and then y-axis y2, which is on the right hand side, what you see is the derivative weight. So as we heat the samples, we start from the 100%, and the sample has start decomposing. As you can see, at a lower temperature, we can see the high temperature volatile oil components start coming out, which accounts to 6.12% of weight changes. As we heat further, okay, we see the polymer decomposition, which is account to almost 51.84%. Okay, at this point, the weight is again getting stabilized. At this point, once the temperature reaches at 600 degree, that's when we do a gas switching. So we switch from nitrogen to air, which further burn up the carbon black which is present in the polymer compound, and then immediately we can see the weight changes of correspond to the carbon black decomposition, which account to 38.96 in this particular case. And finally, what we see is the residue and the ash content, which due to the presence of filler content, which is of 3.031%. So now you can see from this analysis, we can clearly define the composition of the polymeric material. And what you can see here is, what is so peculiar here is that, as you see the polymer decomposition, the derivatives show the kind of a solder, which signifies that which is not a single polymer decomposition, it will be a multiple composition. So the main occasion, since we are using a multi-component system and mix of polymer blend, the standard TGA would be a kind of a challenging aspect. And here another aspect is the atmosphere what we are using. As we all of us know, the decomposition of any polymeric material, whether it's rubber polymer or thermoplastic, is basically a kinetic reaction, and that is purely dependent on the atmosphere what we are using. In this case, we have taken the same rubber compound, tested under air condition and tested in nitrogen condition. So what we see here is there is a clear change. The sample which is tested in air is basically, okay, it is basically of showing a faster decomposition as compared to the nitrogen atmosphere. So which clearly show this particular graph, even though the rubber chemistry is same, the atmosphere has a major effect which has totally changed the decomposition kinetics. So what this signifies that, so the furnace control is something is very, very important. And that's where we need to be very careful in selecting the TGA, how well the TGA, the furnace is going to control the atmospheric, whatever the atmospheric control. And also the task switching is also to be very, fast and efficient. So that is this particular, analysis to show how well the atmospheric condition of either air or nitrogen is going to have an impact on the decomposition kinetics. Now, let's talk about the limitation of standard TGA, and then we can talk about the advanced mode, what is there, which is, it can be a solution for dealing with this kind of complicated situation. Many times, if you look at the standard TGA, you may see a kind of a complex thermal scan with broad weight losses, like what you see here. And many times you see overlapping weight losses with multiple peaks and shoulders. Like you can see here, the sample is showing a multiple decomposition pattern, and also it is kind of overlapping. So when you do the compositional analysis, actually you should know the onset of decomposition, end set, so that you can easily calculate the associated weight loss. But in this case, since the transitions are overlapping, it is a bit difficult for you to easily calculate when exactly the decomposition is starting. Okay, and many times, many occasions, we may have this kind of challenges when you're running that TGA samples. So here comes the advanced mode called high-res TGA, which is basically a sample control TGA. So one should understand the difference between a temperature control TGA and sample control TGA. In sample control TGA, okay, what we are doing is we are regulating the heating rate based on the decomposition of nature of your sample. If you look at the left hand side, here we define the heating rate. So irrespective of sample decomposition or the weight changes, the TGA is going to ramp up the temperature in the predefined heating rate. Whereas on the sample control TGA, as you can see on the right hand side, your sample weight loss also is a part of your control algorithm. So what happens is, the beginning of the run, the sample will be heated at a faster heating rate. As soon as the TGA senses there is a sample weight changes, it will easily slow down the heating rate and allow the particular decomposition to complete. This way it will have a dynamic heating rate. So depending on the pattern of how the sample is going to decompose, the control mechanism or the associated heating rate also is going to change, and that we call it dynamic heating rate, high resolution TG. So what is the improvement you are getting? You are able to resolve those decomposition pattern in a better way. So that's one of the key advantage of the decomposition pattern. So that is what you see here, how the decomposition pattern is resolved in a better manner. And your derivative peaks looks be very, very sharp, and that is the advantage of your high resolution TGA. Here you can see the kind of example for the polyurethane samples. Just for the information, you can see we taken a polyurethane. If you see the decomposition, which is the standard heating orange color curve, the standard heating rate is running by 10 degrees centigrade per minute. The high resolution TGA is starting at 50 degrees centigrade per minute. Okay, so what we see is that very sharper peak, and you can see the clear shift of your decomposition pattern. But look at the derivative peaks. Now the derivative peaks clearly show a sharp peaks. So now we can able to get those decomposition better in a much better resolution. And we can also clearly separate those overlapping events. This is the clear advantage of a high-res TG. Like now, I could show you a simple EBDM rubber car high-res TGA plot. So this is again what you can see here. The green curve is a conventional TGA where you'll be heating at a standard ramp rate of 20 degrees centigrade per minute. Coming to the blue curve, which is high-res TGA, like what you can see is here. Now you can see the blue curve. The derivative mix looks very sharp, and that is because of a better resolution. So in this case, though we started off the heating rate initially at 50 degrees centigrade per minute, as soon as the sample reaches the initial weight losses, which is being absorbed around 420 degrees centigrade, okay, the heating rate will be completely reduced, which allow the samples to, the kinetics to complete, and we allow totally the sample to decompose, particularly that, and that will give a sharpened weight losses. Afterwards, again, once the weight getting stabilized, your derivative is coming to close to zero, the heating rate kicks off again and going to the higher range. Finally, we go to the next level of decomposition. This way, we are resolving the better, the overlapping things, and that also will help us to quantify each weight losses in a better manner, and that which could be of complicated in many of the standard DSC run. And this is the clear advantage of the high-res TGA. Another high-res TGA option we have is a high-pressure TGA. Instrument is giving this high-pressure TGA as model called HPTGA 750. If you see that in a normal TGA run, we always study the material property in two aspects. One is either time and temperature, or we will be changing the atmosphere. But we all know that the kinetics of decomposition also varies with respect to pressure. But pressure is often an ignored aspect. And if you come to the real world condition, the polymeric materials or rubber materials, whether during the processing time, it might be subject to elevated pressure. You can just imagine of extruding the rubber hose, where the rubber polymer material definitely would be exposed to the higher pressure, extrusion pressure. And we may not have the idea how a particular rubber polymer is going to behave at that elevated temperature and the pressure. And that's where that high pressure TG is going to give you. This is offered by TH advanced technique, patented techniques, where we are using some unique technology called magnetic suspension balance, which also facilitate not only do the studies at elevated pressure, also you can use some corrosive atmosphere. You have a pre-gas mixing solution that will connect it to pre-reactive system, gas system, and you can create a very corrosive atmosphere, which is many times not possible on the standard TGA. So this is one of the very superior technology. The benefit what you are getting is that you have a better idea how the particular polymeric material is going to decompose under the higher, not only as a function of temperature, at the same time as a function of pressure. Here I can show you the studies what we have done on the PVC materials. So the blue one is actually performed at the pressure of 1.2 bar. The heating rate is 10 Kelvin per minute. So it's a standard heating rate. And you can see clearly the two step changes of a PVC. One is first it will be evolving the HCl from the things. And then second decomposition is correspond to the loss of aliphatic and aromatic hydrocarbons. Now, same studies we are doing at an elevated pressure, which is at 80 bar. So what we see here is you can see clearly though the onset of reaction at the same temperature, but the studies which we have done at the 80 bar shows the faster decomposition rate as compared to the studies that we performed at the lower pressure. So this clearly signifies how pressure is actually fasten up the decomposition process, and that is the idea we can do. So by using these techniques like high pressure TJ, you have an ability to study the material behavior not only with respect to temperature or time, but also as a function of pressure, which give up as a much more deeper understanding of material, and that will help you, in fact, to design your processing when it comes to dealing with a particular polymer, and that will help you to avoid lot of situations during processing of your particular polymeric material. Another is about the decomposition kinetics. So if you want to understand how the decomposition kinetics is happened for a particular rubber materials, basically this is the ASTM techniques. Pretty much all the DJ can do that. The principle is fly wall techniques, where we would be doing the study at a different heating rate. And as I told you, the decomposition is the kinetics, so it's always depending on the heating rate and the time. So if you are doing at a slower heating rate, the material will decompose at the lower temperature. At a faster heating rate, you can see clearly the decomposition will shift to the higher temperature, and that is because of the kinetics what is involved. And what we do is basically we capture the conversion rate, which is basically as the ASTM technique, at 3 to 4, 6 different heating rates, and then we plot the heating rates versus inverse of temperature. The slope is basically giving the activation divided by the the gas constant. That multiplied by the gas constant will give you the activation energy. So if you wish to understand how is the activation energy of your decomposition, basically you would be doing this faster studies actually. Okay, but now you don't need to do this kind of study. The benefit of it is we have a techniques called modulated TGA. I'm skipping this because this is basically the idea is how you can do this study, understanding of polymer kinetics, decomposition kinetics by single run. As I explained, the normal ASTM techniques which involve multiple heating cycle, but whereas in this case we don't want to perform multiple. In a single heating cycle, you would be able to calculate the activation energy. So that is called modulated TGA. The way it would work is that instead of applying a standard heating rate, we would be applying a modulated temperature ramp. So in a sinusoidal fashion, then there is a backdown algorithm which will plot the activation energy, like in this current thermogram. What you see is a polytetrafluoroethylene. So we can see a simple state changes, and then we plot the activation energy at the real time. As the sample undergo the decomposition, we can see how the conversion head present, what is 354, the activation energy of that particular samples. So that's about the advanced techniques on the TGA. Let's talk quickly about the DSC part. So what is DSC would be doing? So DSC is basically a differential scanning calorimeter. It will measure the how much of heat is being changes with respect to the temperature of your samples. So we put the sample and reference, and then we heat it subject to heating, and then we can see how the sample is undergoing the changes, especially when it undergoes any phase transition. It could be of glass transition, temperature, crystallization, and welding. So then we can measure the associated heat flow of that. So let's say if you see the heat flux DSC, there are two concepts are there. One is heat flux DSC, power compensation DSC. Heat flux DSC as offered by TH have many better advantages as compared to the not power compensation DSC. In a heat flux DSC, you have a same furnace, single furnace. In fact, you have a reference sensor, sample sensor. You keep a few milligram samples on the dripped pans on the sample sensor actually. Okay, and then we will see that how the sample of your temperature of the sample is changing with respect to temperature. So the fundamental equation is two. The heat flow changes would happen due to two aspects. One is heat capacity changes and kinetics. The heat capacity changes is usually basically, for example, as the sample undergoes the glass transition temperature. So what is happening is your heat capacity is going to changes before and after the glass transition temperature. so that the the DSC can detect as a heat flow changes. When, for example, a sample is undergoes some changes with respect to kinetics. For example, we can, let's say you have rubber compound which undergoes some curing process, that can be measured by kinetics as a function of temperature. That also is going to alter the heat flow. So this will give the complete information how the sample is going to change its transition or the associated kinetic transition, and we can able to quantify the heat associated with that particular transition. So, so that's about the Discovery DSC 25,000. So what you can see here is like, if you look at the typical thermograms, so we classify that whenever sample undergo any endothermic or exothermic activities, we can see that, as a shift in the heat flow. So in this case, when the sample undergoes glass constant temperature, which is absorbed as an endothermic freeze, like if in case of crystallization, the curve is going to the exothermic direction. So we see an exothermic freeze. And then if it's a melting, you can see an endothermic peak. Same way, if you are dealing with something like a thermostatic, let's say like a polymer rubber compound, which is undergoing some curing process, then you can measure the cross-linking by measuring the exothermic reaction. Okay. And further, anything in sort of oxidation, you can measure from the oxidation part. Like in case if you wish to say OIT application. Now I can see how DSC is helpful to understand the percentage of cure. Here I presented two curves, so you can see the solid green line curve, which is of optimal cure condition. So how do you understand whether the polymer is completely cured or not, or under cured? You can use a DSC as a technique to determine this aspect. So there are two ways you can see. One is by looking at the glass constant temperature of a cured material. When you look at the green compound, okay, clearly the glass constant is showing at minus 5.27 and the exotherm is showing about 79.3. So what you need to do is you first take the sample, uncured sample, run the DSC, allow the sample to 100% cure, and that measure quantify how much of energy which is required. In this case, for particular DSC samples, we need a 320 joules per gram of energy is required. But what we see here is the optimum cure is 79.3. So if you take the ratio, we can clearly calculate that the green color sample is 75% cure. Whereas the blue compound, which is so even the lower TG as well as higher residual cure. Okay, so this is the second time we are keeping the sample on the DSC, where in the second time we are seeing this thermograms behavior. So coming back to the blue curve, when you account the energy which is higher 145.4, if you take the ratio, the blue color compound is basically it's cured only 55%. So that is the reason we say that the sample is undercured, and that also reflects your glass transfer which is at the lower temperature. So this way you can see how the DSC is really helpful to understand things. So now I want to talk about the advanced mode about MDSC techniques. MDSC is the one of the pioneer and most advanced techniques in DSC. The major benefit here in MDSC is that it will first of all it will increase your sensitivity of detecting a very weak transition. And second major advantage is that it also helps us to avoid that overlapping thermal transition. Just imagine many times you would be running a sample of mix of polymer. It could be a mix of two polymer, and you are trying to understand the glass transient temperature of two polymer, which might be occurring at a close temperature range, which is many times difficult to understand. But doing MDSC, you can able to resolve those things in a much better way. In MDSC, what we are doing is, again, just like modulated TGA, in modulated DSC, we instead of applying a linear ramp, we apply the oscillatory temperature ramp at a fixed amplitude and the period. So in this particular case, you can see if you take a small portion of the the heating ramp, you can see a sinusoidal temperature ramp with the variation of plus or minus 0.42 degrees centigrade and period of 40 seconds. And overall that we are maintaining at 4 degrees and up to the temperature of 290 degrees centigrade. And this way, what's happening is modulated DSC signal will give, I know, three signals. What is total heat flow, which is as similar like a normal heat flow, what you get for the standard heating rate. But apart from that, you get three more heat flow signals. What is reversible heat flow? That is the blue curve, and then the non-reversible heat flow, which is the brown curve. So if you closely look at the thermogram of each individual heat flow signals, you can see the heat flow, the green one, carry all the information. Like for example, in this case, we can see clearly the step changes followed by cold crystallization and then melting. When you look at the reversible heat flow, which is basically only showing the transition which are reversible or thermodynamic in nature. What is glass transition temperature, melting point. So these are the thermodynamic spot which is being easily measurable. Another is the the non-reversible, which is shows all the kinetics event. Even you can see a small endothermic peak which is occurring close to the glass function, which is because of a enthalpic recovery, and then followed by the crystallization and then crystal perfection. So this way, now you are better equipped to detect where exactly the glass function temperature is, and the glass function temperature also looks very broader and very detectable manner. So that's what we are talking about here. The MTSC can give you three signals total, which carry all the transition. The reversible heat flow, which is only going to show the heat flow which are related to heat capacity, and non-reversible, which are going to take all the transition which are due to the kinetics, could be of evaporation, crystallization, curing, all sort of that sort of transition. Now I'm going to show you, this is my last application. I'm going to show you how a practical situation the moderated DSC is going to be helpful. Many times polybutadiene, which is one of the important rubber compound which is being used in tire industries, and we generally mix that polymer with other polymer. Okay, so it would be sometimes very difficult to quantify how much of polybutadiene is present in a particular mixture. So the DSC can be used for that purpose. So when you run the 100% butadiene, what we see here in this, we can clearly see a glass function temperature which is around -100. So in DSC you have an ability to take it to the negative temperature. In this particular DSC, the DSC run is performed with the help of liquid nitrogen. So we started off from -160 degrees centigrade, and then we can see a clear step changes because this is 100% polybutadiene. So we can able to see that, and then again as you heat further, the amorphous compound convert to crystallize, and as you heat further, you can see the endotherm which is due to the melting, and same is reflecting in the heat capacity signal also. You can see the heat capacity is increasing above the glass transition temperature. Now, when you come to the low content polybutadiene, because this is the unknown samples, but we want to understand how much of polybutadiene is present in this particular polymer. When you look at that, it is very difficult, nearly impossible to detect those glass function temperature which correspond to the polybutadiene. Now, what we are doing is the same samples we've been testing in modulator DSC. Okay, and now you have the ability to clearly plot the reversible heat flow, because as per our experimental condition, we need to see the reversible heat flow, which is going to show the transition of especially the glass function temperature of the polybutadiene in that. So we are plotting here the reversible heat flow against reversible CP, also against the temperature. And what we see, we could clearly see the step changes, and also we quantify how much of heat capacity changes. If you go back to my previous slide, so in this slide, if I hope you are all able to see this slide. So if you see the step changes is well pronounced, and we can see clearly that, and what we are getting is the range of 0.336 joules per gram. And this is the total heat capacity of 100% polybutadiene. When it comes to now, we are measuring a 0.022 joules per gram degree centigrade. If I take this average, okay, I can clearly quantify even a 6.6% polybutadiene, which is present in the polymer, accurately by using modulated DSC. So this is the one of the key advanced benefit of this, modulated DSC techniques, and that is what you are getting out of this analysis. With that note, I summarize my presentation. As I highlighted, TA Instruments is today one of the recognized market leader in advanced thermal analysis equipment. We have a large selection of thermal analysis products and techniques available for a thorough material characterization, and we catering to broad application area, whether it is polymer, pharmaceuticals, life science, energy. We are offering a complete, a comprehensive solution for the thermal analysis, your thermal analysis problems. And we also committed to, innovate the new technology. So that's what we are talking about. Some of the techniques like FDSC and all those techniques. Okay. With that note, I'll summarize my presentation. I thanks for these wonderful opportunities, and I would be happy to have any questions if you have. Thank you. Over to Parag.
Okay, that's the presentation on the advanced thermal characterization techniques of rubber materials by Dr. Raj Ganesh. It is expected, it was longer than expected. Let's invite Dilip Dupia again from the Alpha Technologies to make a presentation on the premium RPA sub-zero technology.
So once again, say good evening to all attendees of the rubber industry news hour from India. So as introduced by Peram, my name is Dilip Dhupia, application specialist, Alpha Technologies. I'm responsible for India and Southeast Asia, say customer training and say new application development and and conducting training programs and conducting the seminars for Alpha Instrument. And say with the help of my team at say different organizations, I just acquired 25 years of experience in the field of research and development, shop floor processing, and and rubber product in industrialization. If you are say passionate about the low temperature properties of rubber, then I think say this is for you. And then please stay tuned till end for better insights. So we will begin our journey with overview of alpha technologies, followed by continual improvement definition, then through RPA sub-zero technology development path, the development need and the development focus, then sub-zero technology works and the technical specifications for the sub-zero technology, and the precision dynamic modulus technology, and in the end I will show you the data comparison with dynamic mechanical analyzer. So Alpha Technologies, a Roper technology company, is dedicated to work closely with rubber industry to improve and enable performance, value, and safety to customer. As the recognized leader in rubber and polymer rheology testing, we continues to innovate and advance with the best in the testing solutions. Say for example, ASTM D5289, when it was first introduced, it was based on the our moving die rheometer, and it has revolutionized the rubber industry by improving the productivity and setting a new standard for quality control. So Alpha Technologies, the presence is there around the globe. Here you can see we have 150 plus global direct associates then 50 plus field service technician, and then 25 plus the customer and yeah, and technical support staff. We have 7 degree application engineers. I am one of them, and our calibration services are ISO 17025 certified, and around the globe we have more than 18,000 instrument installed globally. And we at Alpha Technologies they take our role very seriously by providing the sensitive instrument to the rubber industry. So because our customer safety is at risk. So a top rubber product means manufacturers in the world they trust us to means provide repeatable, reproducible, and reliable results and a timely service to keep up the instruments. And I think it is appropriate to start any discussion on the process improvement and quality control with a quote from W. Edwards Deming. This quote gets to the heart of what everyone in the process and manufacturing industry knows. So, building a better gauge to catch bad product before it goes out of the door is not quality. Almost all of the quality system and tools are set up in this way, like filters to keep that product out from reaching the customer. But the real quality comes from deploying systems that are continually reduce variations in the production process such that that product is not produced. So let us start our discussion on RPA Sub-Zero technology with a brief history of RPA. RPA continual improvement has been about variance reduction. In early 90s, Alpha introduced RPA 2000 that was reliable and robust and the first generation technology, then followed by the premier RPA. In that, we improved the dies and seals, and we improved the sampling rates, and we introduced flexible architecture in the software, and we standardized at that point of time latest technology, and we also enhanced our LAOS. LOS is large amplitude oscillatory shear. And our third development was Premier RPA Plus. It accounts for the material and die depth variation, account for the sample shrinkage, and it improves the on sample shrinkage. And the latest launch is Premier Sub-Zero technology, which is aimed to replace cumbersome DM testing and improve reliability of post-cure subtest over DMA, and it can go up to negative 25 degrees centigrade. As you all know that the DMA test, it requires a minimum of 18 hours time after the sample preparation. So RPA, though we are not giving any 18 hours for sample stabilization in the in, uh, testing. So the need of development is to equip rubber industry with a tool to quantify the rubber compound via predictive testing at shop floor, and this will certainly help in reducing the cycle time for sample submission to OEM and to assist the industry striving to attain first time quality. Above all, to provide an amicable solution to industry with alpha reliability. Then, after defining the needs of the sub-zero technology, then we decide what should be our focus. Our focus is to define one single test to qualify the rubber compound processing properties, cure properties, and tire performance properties indicator. And the second focus was liquid nitrogen free cooling that ensures the safety of laboratory personnel and the determination of real-time data based on the actual shape factor of sample at test temperature. And last but not least, to bridge the gap between the shop floor mixed compound and R&D developed rubber compound data. Thus, Sub-Zero technology optimize the amount of sample to be used for testing, then reduces the process of testing time. Say for example, DMA requires minimum of 18 hours of sample stabilization after sample preparation to the test and eliminates the need of DMA. Thus, RPA Sub-Zero is one-stop solution that all you need for quality control and R&D testing for processability, cure properties, and the tire performance laboratory mispressure. It uses the same rubber sample, thus it saves energy and efforts with alpha reliability, and it encompasses the lower capital spending. On the right hand side, you can see the graph between the data comparison graph between RPA and the DMA. The green one is RPA, while the blue one is from the DMA in tension compression mode. And in one single test, you can determine the laboratory predictor for tire performance on ground of snow traction, wet traction, dry traction, and rolling resistance. Now you let us look at the specification for RPA Sub-Zero technology. The frequency it ranges from 0.0016 to 50 Hz. The strain it ranges from 0.07% to 1255%. The temperature is from negative 25 to 230 degrees centigrade, and the maximum temperature ramp rate above room temperature is 1 degree centigrade per second, and the maximum die cooling rate above room temperature is 0.5 degree centigrade per second. And you can see here how we are going to the sub-ambient temperature is from 60 to 30 degrees centigrade. It cools down at a rate of negative 7.5 degrees centigrade per minute, while from 30 to 0 degrees centigrade cools down at a rate of negative 5.5 degrees centigrade per minute, and from 0 to negative 25 it cools down at a rate of negative 2.5 degrees centigrade per minute. So we are having very controlled cooling of the die, and we can attain temperature accuracy of plus or minus 0.2 degrees centigrade at negative 25 degrees centigrade temperature. And we determined the reproducibility of our started compound is less than 10% at sub-zero temperature, and the average repeatability for compound at negative 25 degrees centigrade is less than 6%. Then the torque range is from 0.01 to 225 dc Newton meter. The torque, temperature, and frequency and strain are the measured data, while the calculated data are the modulus, the compliance, the torque, the 10 delta, and the real and imaginary component of viscosity with the complex component of viscosity. The data storage is basically SQL database, and on the ground of testing standard, it meets ASTM D1053, D5289, D6048, D6204, D6601, D7050, D7605, and ASTM D8059. Now let us discuss about the PDM technology. that we call it as a precision dynamic modulus determination technology. This technology is to compensate for sample shrinkage at low temperature. As you know, when we are curing any rubber compound at a high temperature of, say, for example, 780 degrees centigrade, and when we cool down the high temperature, the rubber samples shrink away. So what we did is that we just incorporated a technology which will compensate the shrinkage of the sample. at, at the same time it will actively monitor the material geometry, and the same geometry we are using for modulus calculation. So we are calling it as a precision dynamic modulus. So the PDM technology uses real-time shape vector for calculation of modulus. Since the shrinkage is being actively monitored, thus the shrinkage is actively compensated to reduce the sample slippage. So whenever we are actively controlling the sample, actively monitoring the sample slippage, so that's why we are able to minimize the sample slippage during dynamic deformation. So this technology has reduced the COV for cured SBR by 49%, and for uncured SBR, the storage modulus, the COV has been reduced by 81%. So PDM, huge improvement in data is observed, and on the right hand side you can see the specification band has been reduced a lot for uncured SBR compound, and as well as for the cured SBR rubber compound, and you can see the accuracy and the precision of the data is improved with the help of precision dynamic modulus technology. So in the precision dynamic modulus technology, we are using the actual shape factor at the test temperature. So we are giving the most accurate rheological data in the world for the modulus values. Now I wish to show the a test example from the Premier RPA and the DMA, that is rubber process analyzer, and DMA. Here all the test conditions they remain same except the mode of deformation. In RPA, the mode of deformation is torsional shear, while in DMA it is tension compression. Now you can see at the data at 30, 40, 40, 50 and 60 degrees centigrade, the R square value is 0.99. For loss modulus, again it is very good correlation, and when you look at the ratio of loss modulus to storage modulus, you can see the values are all almost similar from RPA as well as from the DMA. Now, what is way forward of us? So in the 3 decades after introduction of RPA 2000, the RPA has come a long way, and we will continue to strive to further improve our process, product, and its performance. So, and if you have any questions, you please write me to dilip.dupia@alpha-technologies.com. And thank you very much for patience hearing, and thank you very much.
Thank you, Dilip, for the good presentation on the RPA. Let me take over the screen. Okay. Guys, if you'd like to ask any questions to Dilip, please post your questions in the question box, and we will address them in the Q&A session. Now the presentation is on the rubber process analyzer testing technology for high shear and low temperature testing by Ralph Berlin. He's from the Montech. I think Ralph is all his professional life is with the rubber testing instruments, so a lot of experience. Let's welcome Ralph to make a presentation on the rubber process analyzer testing technology for high shear and low temperature testing.
Yeah, thank you very much for your kind introduction. My name is Ralph Bäuerlein. I'm an application specialist with Montech. We're a German rubber testing and instrumentation company. And today I want to report to you about our latest development about high shear and low temperature testing with rubber process analyzers. A quick introduction about Montech. We're a privately owned company originating from Germany, where we have currently 3 manufacturing sites, and our company has been growing since its inception in 1998, spanning over 60 countries all across the world with about 260 directly employed people. We're currently manufacturing in our 3 German and 1 US manufacturing locations about 150 testing instruments per month, solely dedicated to the rubber industry. We have a global network of sales, service, as well as showrooms in Germany, US, but also all other countries with major rubber companies present all over the world. So today I want to report to you a little bit about dynamic rubber testing. Rubber process analyzers have become state-of-the-art equipment, not only in R&D, but also in quality control in rubber factories. Basically, the application area of rubber process analyzers can be classified in 4 different segments. Utilizing the RPA as a raw polymer tester to assess, for example, viscosity, molecular weight distribution, branching of polymers, gel content, as well as polymer aging properties. Furthermore, RPAs have been used to check processability, to simulate production processes such as milling, extrusion, to correlate, for example, to mold flow, die swell, process viscosities, but also to dispersion. Then RPAs have been used basically since their inception as advanced cure meters to, of course, measure cure times, cure rates, cure conditions, reversion at isothermal as well as non-isothermal conditions. And the last and largest application group is to utilize dynamic rubber process analyzers as dynamic mechanical analyzers, dynamic mechanical testers, or dynamic thermal testers to assess after cure modulus properties, elasticity, viscoelastic properties, or correlate to final product properties such as heat buildup or damping, especially interesting for the tire industry. Here, however, there were limitations. Limitations in terms of the shear rate range that RPAs could cover, but also about the temperature available. Basically, customers had to utilize multiple equipment, TGA, DSC, DMA, RPA, to get a full picture and a full fingerprint of a certain batch or material. Also, the RPA was not successful in covering all related shear rates to rubber relevant processing steps, especially injection molding, extrusion, mixing, calendering processes had been always a challenge to be simulated with the RPA due to the shear rate limitations in oscillatory mode. Therefore, Montech has recently introduced the Advanced Applications Package. This is a new drive technology, a new control technology for rubber process analyzers, not allowing only to use the instrument in oscillatory mode, but also using the RPA as a rotational rheometer. So it's a combined system that can do all the classic things the RPA was always capable to do, with oscillatory frequencies up to 100 Hertz, strains up to 5,000%, that typically translates into shear rates of about 100 per second. However, with the newly added capabilities of continuous rotation of the lower die in a rotational mode, shear rates up to 750 per second. So it means a 7.5 times higher shear rate range can be achieved. This adds the capability to classify and simulate successfully also high shear process, once again, such as milling, calendering, injection molding, and extrusion. Large amplitude oscillatory shear has been now around for several years, but this is the next step, expanding the capabilities of RPA systems. Combined with this, variable preloads, programmed as drive offsets or pre-strains, can be set for every subtest method, closely simulating the real application environment of your test sample or of your final product. And once again, this system also adds one more time to the layer's capabilities for high shear testing. All this paired with our normal force control system, eliminating all die gap variations, wall slip measurements are possible. So looking at the capabilities of the instrument, typically MDR instruments were only used for measure curing. RPAs were used to look at low to medium shear processing. Now, with our advanced application package, new processing techniques can be successfully simulated in the RPA. Combined with our low temperature MCool -40 system, even lower test temperatures down to -40 degrees C are possible. This system is enabled by a new direct drive motor, a motor that we manufacture in-house, tailored to the requirements of the RPA. The lower die can oscillate, but also can continuously rotate. The lower die can be moved upwards and downwards, varying the die gap, controlling the sample to a constant pressure to account for any die gap change or sample shrinkage. To always have, with profiled dies, complete slippage-free test results. However, for specialty purpose, we offer over 40 different test die arrangements. Test dies can, for example, be flat dies for composites, for resins, but also can be flat or grooved, flat or conical polished dies to intentionally measure wall slip. By comparing data with and without wall slip, the exact extrusion behavior of materials slip in the extrusion barrel could be tested and quantified, providing important information on the material's viscosity during high shear processing. Other processing techniques and measurement results include high shear heat buildup and thermal conductivity measurements, which can be realized by simply switching off the heating control system of the instrument and measure thermal conductivity from the high shear lower die to the upper die. This is not only suitable for rubber materials, but also, of course, for thermoplastic materials, thermosets, thermoplastics, and our new application group, also food, can be tested with rubber process analyzers. This system is complemented with our unique die pressure management measurement and control system with a controlled closed loop normal force, not only controlling the die gap, but closely controlling the normal force on the sample. Here we see a comparison of high shear testing where we measured two samples which, according to the manufacturer of or compounder of the material, should be identical. However, we can clearly see high shear differences. First of all, we see a general decrease in modulus on viscosity on the left material, as well as a much quicker, as a much lower heat degradation, whereas the picture on the right shows that the material at high shear rates above 100 RPM quickly degrades because of a much lower level of molecular weight distribution and long chain branching, causing a much quicker heat buildup and destruction of the sample. This now allows us to simulate complex test sequences. For example, we have looked with one of our customers at injection molding process, where material passes through different temperature zones, as well as experiences different shear rates while it's traversing through the machine. First, the material is fed into the injection barrel. Then we have our high shear injection phase, where the material is pushed through a nozzle into the mold and then our temperature increase and the actual molding cycle. Now, looking at the material response measured with the RPA, with advanced applications package, we see stress relaxation while feeding at lower shear rates, and then the actual 80 per second high shear injection phase causes another real major relaxation, and of course also the heat up causes another change in the elastic torque. And this, combined with our molding phase, allows now to get a full rheology profile of not only the curing, but the full process the material passes through, gaining a much better understanding of material properties, but also for a tighter control of your process, detecting batch-to-batch variations before they translate into processing errors. All this can be complemented with one of our cooling or advanced heating systems. Typically, our instruments range from ambient temperatures to 235 degrees thermal range. Now, with our MCOOL 10 system, a vortex cooling system specially developed for medical applications, for example, silicones, allows cooling of the test dies sub-ambient to a lowest temperature of 10 degrees C. This is a very cost-effective system, not requiring any additional space as it's fully integrated into the machine. And then we have our MCOOL 40, which you can see here on the right, which is our chiller system for sub-ambient cooling down to minus 40 degrees, reaching almost glass transition temperature for several polymers. As well as also we offer high temperature options for the resins, prepregs, thermosets, and composites up to 350 degrees C. Most of the manufacturing processes in the rubber industry are not isothermal. They're non-isothermal. What this means is the material passes through different temperature zones, which we see here, the material getting heated up in about 3 minutes time from ambient temperature to 160 degrees. And the same can be simulated with a rubber process analyzer to understand curing under these specific thermal conditions, as well as also changes of elasticity and viscosity. All this can be combined to complex processes, either in different ramps or with different steps, simulating even the most challenging thermal profile. Or if you have a recorded profile, our Mon Control software can directly read your thermal profile from a file and process it in the instrument. And that brings us to a couple of applications for our MCOOL-40 low temperature cooling system. Here we have an example where we measure glass transition temperature successfully with the RPA. Or we have been looking at the plasticizing effect of oils, different oils or different quantities of oils in the recipe, changing significantly glass transition point and glass transition temperature. All this is only possible with our MCOOL-40 options, as we have the widest thermal range covered in the market for low temperature RPAs. Especially for the tire industry, this system has been found very useful. We have installed more than 70 of these systems at our global tire customers, mainly related to tire labeling requirements, measuring rolling resistance, but also rain or wet traction and ice properties. All this can be combined now in one single machine, in one single reliable test. Data acquired also allows us to create advanced cure kinetics models, meaning by having rheological data available at different temperatures, we can easily calculate order of reaction, rate constants, incubation time, and most interestingly, also activation energy. This allows us to create normalized cure curves as well as Arrhenius plots, either for isothermal conditions or also, of course, for non-isothermal conditions. This can be used to also simulate processes. Here, after running the cure test, we have loaded a thermal profile of an autoclave of one of our customers and then compared his rheological data, and we found that his production process was set up perfectly right, as while opening the autoclave, he was reaching exactly 100% cure, avoiding any reversion, avoiding any lost process time and money lost. This can be expanded to non-isothermal testing by running either heating or cooling ramps and loading them into the cure kinetics models. Also, activation energies for different states of cure, different cure times can be calculated. And last but not least, also this data can be used to do a 1 or 2 dimensional cure simulation. Here, for example, for a 20 millimeter thick rubber sheet, based on the rheological data, we can tell how fast at which position of the part the material will cure, and based with this data, define optimum curing times for parts and geometries. My last topic I want to look at is the nonlinear material response, as we are now with our new systems are capable of even running higher shear rates, covering a wider testing range. The nonlinear material response is becoming more and more important. Here, the input is still a traditional oscillatory or steady shear, means continuous rotation input from the lower drive system. However, our material response is no longer sinusoidal, but a distorted sine wave. This, we have done extensive research and added Fourier transformation rheology by looking at higher harmonics, so means frequencies higher than the original frequency, but also by plotting this data in a stress strain versus strain rate format, calculating long chain branching index. Based on these two models, we are now able to create simplified reports in seconds, providing you a full overview of the nonlinear material response of your items that you are testing, quantifying the level of branching, long chain branching, as well as also molecular weight distribution. So to summarize, low temperature testing creates new possibilities for quick tests on raw materials and compounds, complementing traditional test methods. Updated testing methods are required to keep up with new raw materials and processing techniques, especially high shear mixing, high shear milling, extrusion, injection molding. And Fourier transformation rheology is a required tool actually to understand the data derived from these tests and in order to quantify and correlate to your molecular structure and long chain branching. So to summarize is that all these new technologies allow you to, within one single test of only a few minutes, create a full fingerprint of your material, dramatically speeding up your quality control processes by eliminating other traditional test methods, but also helping you in your R&D to quickly and easier get the right path and understand your new developments and formulations and their properties. Thank you very much. It was a pleasure to speak. I'll be available for questions later on. Thank you very much.
Thank you, Rolf, for the excellent presentation on the RPA. Please stand by. Guys, if you'd like to ask any questions to Rolf, feel free to post your questions in the question box. You'll address in this one during the Q&A session at the end of all the rest of the presentations. Now the presentation is on the carbon black and rubber filler characterizations by Mr. Andrea Mirandola. Is from the High-Tech Luxembourg. He joined the High-Tech Luxembourg in 2016 with the role of the manager of the testing technologies in the fielding activity. And since January 2022, his role is Chief Business Developer of the High-Tech Luxembourg. Let's invite Andrea to make a presentation on the carbon black and rubber fillers characterization.
Hello, everybody. And welcome to the Rubber Industry News Hour. My name is Andrea Mirandola, and in the next slides, I will introduce you to our company, High-Tech Luxembourg, to our product portfolio and offered services. We will focus on testing equipment to characterize carbon black and other rubber fillers. So let's introduce our organization. High-Tech Luxembourg is a private-owned Luxembourg company. We offer high technology solutions covering 4 different business areas. We will focus today on equipment for testing and measuring of physical properties of carbon black and other rubber fillers. The company was founded in 1986, and since then, High-Tech Luxembourg is operating in the testing equipment field. We are a small medium enterprise with over 50 employees, most of them engineers or with a technical profile, with different competencies which cover 6 main areas: software and ICT, project management, physics, mechanical engineering, electronics, and high frequency. We are customer focused and our objective is to deliver innovative and high added value products and services. The motto of our company is market oriented, client centric, and technology driven. Our company holds several certifications related to the quality management, environmental management, occupational health and safety management system, and social responsibility. We participate in several work groups and we are active contributors to the ASTM. Our customer base is quite international and our product find application all over the world in the R&D and quality control labs of all major producers of carbon black, tires, and rubber goods. We serve our customer directly from our headquarters in Luxembourg, where also our production is located, or through a network of local agents and partners. Let's now start to talk in detail about our products and their application. I would like to note that each of our instruments operates following the principle of one or more ASTM standard test methods. So this is our main reference. The same equipment can also be compatible with the respective test methods published by other normalization bodies, such as ISO or the Japanese industrial standard. When we focus on ASTM, we should precisely look at the Committee D24 on carbon black. The committee is organized in subcommittees, and each one of them is focused on a specific topic related to carbon black. Not all are related to high-tech testing equipment. The ones interesting to our talk are the D2411 on carbon black structure, D2451 on carbon black pellet properties, and the 2431 on non-carbon black components of carbon black. We can also find other references that are interesting or related to our equipment within the ASTM in the D11 committee on rubber that you will all know very well, on the D36 committee on recovered carbon black. This last one is a relatively young committee created to support the growing recovered carbon black industry. Recovered carbon black, or RCB, is a product recovered via thermal decomposition from rubber goods which contain carbon black, basically from end-of-life tires, but not only, and can be used in certain selected application as a substitute of virgin carbon black. Some of our equipment are used for the characterization of RCB as well. At High-Tech, we have a portfolio of 8 products in total. 3 products are related to the characterization of structural properties. 2 units are used for the determination of pellet properties. 3 units are used for the determination of sieve residue. Sieve residue is one of the non-carbon black components of carbon black. We will see in detail each unit or each test method. But at the end, the target is to characterize the material, this material, carbon black, but not only, also other rubber fillers, and be able to predict in rubber compound performance or prevent defects. Then you see the first 3 products are related to structure properties. We have the compressed volume structure tester, the DABS oil absorption basic system, and the carbon black press HCBP. The carbon black press is not exactly a testing equipment, is more a sample preparation tool. We will see in detail what is used for later. Then we have the IPHT, individual pellet hardness tester, is used to measure the individual pellet hardness tester. We have a pellet powder mass strength tester. And the last three units are sieve residue testing devices. We will see also the difference between the different devices in the next slides. Let's talk a little bit about structure properties. Carbon black structure is the quality of irregularity and deviation from sphericity of the shape of a carbon black aggregate. This is the definition that is coming from the ASTM standard. Basically, when we measure or we look at the void volume, internal void volume, the aggregates, the greater the measure of the internal void volume, then the more complex, open, and branched the aggregates within the sample are, and the higher the structure is. We have two main characterization methods that we can use. We have the oil absorption number, the acronym is OAN, or a void volume analysis. Basically, the difference between the two is that in one case, the oil absorption, we fill the void volume we mentioned before with a liquid. That is, in this case, oil. We have different type of oils, but it's always a oil-based liquid. And in the void volume, we compress the material and we measure the void volume. So we measure the variation in volume of the material. In industry, we can also find a third method of characterization, that is the COEN, so the compressed sample oil absorption number. And simulates this third method. The typical breakdown carbon black may be exposed during the mixing process with the rubber. In this case, the carbon black is first compressed in a press, and its structure is measured again using the normal oil absorption system. The difference between the regular oil absorption and the COEN gives you an estimation of the stability of the structure of carbon black, stability during the mixing process. So here we have some equipment we mentioned before. So in the OAN test, the oil is added at a constant rate to a sample of carbon black. It's used sometimes also for silica, this test method. The mix of carbon black and the oil changes from a free-flowing state to a semi-plastic agglomeration with an associated change in viscosity. And with this viscosity increase is the trigger that is defining the end of the test. Yes. The volume of oil that we add per 100 gram of mass of carbon black is the oil absorption number. This you can see in the picture is our current version of DAPS oil absorption testing equipment, and it was released in 2021. And compared to the previous version, it's improved in design and ergonomics, and complies with the most recent technical safety standards. So we did an upgrade in the electronics, in the control units, and also in terms of safety and ergonomics of the machine. On the right side, you see the COEN test, where the carbon black is first compressed at the target pressure of 165 megapascal, and in a specific press, and then it is again measured on the OAN machine. So in this case, you will not need only the DAPS, the OAN tester, but you will need also a carbon black press. Our carbon black press is a hydraulic press engineering for this specific purpose, and considered to be placed in a lab. So is a compact design compared to other presses that you can find on the market, or mechanical presses adapted for the scope. And we designed the machine with a particular attention on health and safety aspects. The compressing chamber is completely confined and accessible, opening a transparent door, so the operator can control all the compressing operation. And on the back of the machine, we provide also a shutter, so you can connect the machine to the system of the exhaust in your lab. So this avoid the need of a special hood for the press, because the compression operation is a bit dusty. It's creating some dust in the environment. So you need a lab hood, or in this case where the compression area is all confined, you can use the shutter that we provide as a standard. We go to the next slide and to the third unit that is used for carbon black structure characterization. In this case, we have a void volume tester, and we measure the compressed volume of a weighted sample as a function of pressure applied. The standard pressure applied is the 50 megapascal, but our equipment can go much higher in terms of applied pressure. So for a R&D purpose, a user can decide to test also higher pressure. The key features of our void volume tester are controlled compression, controlled decompression. This is a feature that Hi-Tech has patented. We have a compression chamber available in a ½ inch, 1 inch, and a special 1 inch for conductivity measurements of carbon black. So the standard is normal ½ inch, but we realize that our customers are appreciating also the 1 inch, because sometimes you have carbon black in fluffy materials and not in pelleted, and it's much more convenient to have a bigger compression chamber to fit a larger volume of material. With our equipment, you can measure void volume versus applied, transmitted, or geometric mean pressure, the residual void volume, which is correlated to COEN structure, material friction losses, which are reflecting in some way NSA and STSA surface. And with a special option, you can also measure the electrical conductivity of carbon black, which is really interesting for carbon black producer, which are also operating in the battery business. It's not really interesting for rubber, but for battery business is quite interesting. Also, the tires producer are interested in this feature, I must say. We go now to the pellet properties. The main or the most important characteristics of a pellet is the individual pellet hardness, which is defined as the force required to fracture or crash a carbon black pellet. This is an important characteristic in rubber processing, because it's influencing the processability of carbon black filled compounds. So when you in your compound you will have 2 hard pellets, they are not breaking properly during the mixing and generating a bad dispersion. And when these pellets are too soft, they can be in carbon black cluster or smashed powder during the compounding or during the transportation, and generating a possible congestion of the conveyor system, or also in this case a poor dispersion in the compounding process. The second characteristics when we speak about pellet properties, the mass strength. Mass strength is the measure of the tendency of carbon black pellets to pack together and to influence the flowing in a bulk handling system. This characteristic is affected by pellet hardness, size, shape, and especially by fine contents. When you go on the specific on the test method to measure the pellet hardness, the sample need to be first sieved to collect a a certain fraction on the uniform size, say between 1.4 and 1.9 millimeters. The sample is then transferred into the tester, and the tester is collecting each single pellet, and each single pellet is pressed against a force capture system. Under the pressure applied, the pellet will either break with a rapid force drop, or will reduce in diameter. The individual pellet hardness is the maximum force prior this force drop we mentioned, or when it's not breaking, when the diameter is reducing until the 90% of the initial diameter, whichever of the two conditions come first. Our equipment is let's say an equipment with that is reflecting more than 25 years of experience in the construction of a pellet hardness tester, and is this the last version that was which was released in 2018-2019, and the coming mounted on a damping table, which reduce the influence of industrial vibration on the precision of the measure, and is integrated with a sample carousel, which can allow the operator to load on the machine up to 14 samples and measure up to 14 samples without operator intervention. The output data of this equipment are the pellet hardness and the pellet diameter. And of course, you will have also statistics about the pellet characteristics. Basically, you normally measure the standard is an average of 50 pellets or an average of 20 pellets. So you will get as an output the average, the hardest 10%, 3 or 5 pellets, and the softest pellet, and you get also the individual data for each single pellet measured. This is what you get in on the test report of each measurement. We go to the carbon black pelleted mass strength. This test is the machine is let's say quite simple because it's a standalone machine, tabletop size, which do not require any control PC because all the function and operation are controlled via control panel and a 7-inch display that you can see on the picture. In this test, the carbon black sample is placed in a compression chamber and is pressed with a plunger for 10 seconds, after which the bottom of the compression chamber is open. Basically, you can fill this cylinder with material, you compress, and then the end you open this drawer at the end of the test. You have then two options. In the first option, the material is flowing freely. So that means that you didn't reach your pack point, and then you have to repeat with different setup of pressure until a ring or a bridge is created inside the compression chamber. So when you are able to pack completely or partially your material, means that your packing point or is reached. The force you have used to reach this result, expressed in Newton, is called the mass strength. We have then the products for sieve residue testing. There are many tests and parameters which are related to non-carbon black components of carbon black. ITEX products falling in this category are related only to the sieve residue determination. That is also in the jargon vocabulary is called also grit content. Basically, the sample is washed or flushed with water through a wire mesh screen, which can have different sizes, agreed between a supplier and buyer, or just on the choice of the supplier, until so this sample is washed until all that remains is a non-carbon black residue. The residue or the sieve is conveniently dried in a stove or oven, and the weight is taken. And the sieve residue of the original sample is the material that is left after washing and after drying. And this is expressed in a milligram per kilogram or ppm. This sieve residue data is important because it may relate to the surface appearance of mechanical properties or also the mechanical properties of the compound. In some cases, also considered originated by contaminations. So when the case, further analysis can be conducted to determine what is the origin of this contamination. And the carbon black manufacturer can have also some indication about the status of his production process or equipment. You see here, I put in two categories. We have three different apparatus for sieve residue. Two apparatus are for carbon black in rubber application. The commercial names of these two apparatus are A2000 and NDA vacuum. And the one on the right is not related to rubber application, is originally created for pigments, but it is commonly used also for rubber filler which are not carbon black. For example, silica, or for other rubber components like zinc oxide or titanium dioxide on any other powder material, let's say that. So it's the most universal among the three products. Let's see then what is the difference between A2000 and the A vacuum. So if both equipment are supposed to be used in rubber, carbon black for rubber application, why should I take or adopt one or the other? The A2000 is working with a principle that is described on the ASTM D1514, and where the material is washed through a sieve. It's a very compact dimension, and it's a small machine. It's just less than 50 kilos, and the sample you can measure is 100 grams. The sieves have a small diameter, is 50 millimeters, and we have three different kind of sieves. The plastic sieves, is a stainless steel mesh, but with the plastic ring. We have a stainless steel ring and a stainless steel ring with a impact tongue. This method is used for carbon black for general rubber application. The second equipment, the NDA vacuum, is more recent. The first edition of the test method is 2011. And the test method we refer to is the ASTM D7724. It's a relatively big machine, and one of the advantages is that in this case you can measure bigger sample of material. So starting from 500 grams, that is the standard according to the test method, up to approximately 1 kilograms. We have also bigger sieves in this case, which have a diameter of 100 millimeters. This test method was developed initially for carbon black, used in a mechanical rubber grades application. And the NDA vacuum is a useful tool to predict surface defects caused by insufficient dispersion of carbon black of APDM extruded profile. So the mechanical rubber grades or mechanical rubber goods industry is likely adopting the vacuum, while the general rubber application is likely adopting the A2000. Together with the machine, we are able also to offer sieves of different size, starting from 20 to 800 micron, and we can also offer a certification of the sieve mesh provided by the fabricant of the mesh. At Hightech, we also consider the customer experience, the customer service, and after-sales service an important part of the success of our business. And the services are important as important as the product. we act accordingly, and we are able to offer custom tailored services. This can be commissioning and startup of the machine at customer premises, can be training offered online on the customer premises, can be maintenance, preventive or troubleshooting, and in some cases where we already have experience, it can be custom development. Our main markets, you can imagine, are carbon black, tiles and rubber. Recovered carbon black is a growing market, and silica and other fillers. In case you have any question, feel free to ask in the discussion after the presentation, or you can text me. You can search on our website. We have a hitech.lu/testing technologies, or we have shop.hitech.lu. You have this email, sales@hitech.lu, where you can type your question and ask. And we have a great network of local partners, especially in India, where we have local partners in China, India, Korea, Pakistan, Sri Lanka, Taiwan, Thailand, and Turkey, but not only. Thanks to everybody for your attention.
Okay. Thank you, Andrea, for the presentation. The next presentation is DMYOV, oscillograph for testing elastomer properties. This presentation was given by Dr. Ismail Salted from the Taudi. Dr. Ismail, he founded and owns the Taudi company based in USA. Actually, he did his PhD in the University of Akron and chemical engineering in 1974. And Taudi company has served the global rubber and plastic industry, providing high quality service and technical issue resolution in testing through the elderly mechanical oscillograph as per the ASTM D945 12 test method. Most recently, Taudi has designed and launched its next generation testing machine, DMYOV, elderly mechanical oscillograph. Let's welcome Dr. Ismail to make a presentation on the DMYOV oscillograph.
Thank you. Let me give you a little bit of history. This goes back to my years at University of Akron under Dr. Alan Gent and also Dr. Maurice Morton, who was the director then. I did ask them a question about how to characterize dynamic properties of rubber. This was way before what we now have in the market. At that time, I heard that Yearsley oscillograph was the characteristic dynamic tester of viscoelasticity of rubber. Viscoelasticity was just coming into play in this industry. So at that time, I did search for Yearsley and found out Dr. Felix Yearsley, who was employed by DuPont, and he designed and developed this oscillograph, mechanical oscillograph, and also had ASTM D945 test method implemented. And then I got in touch, found out Dr. Felix Yearsley unfortunately passed away. So we bought out the company's assets and carried on. During the years when Dr. Yearsley was producing this oscillograph, he sold it to well-known companies in the world. I mean, aeronautics, tire, NASA, and many others. So it was well established that this equipment could characterize the rubber properties at low frequency, but definitely at the time of testing, it could generate the natural frequency and all the parameters at that natural frequency. So as we carried on, we have developed a new model, which we call DMYO number 5. Our original model was AYO number 4. The DMYO number 5 is a bit different. Taudi Co. is a U.S. corporation in Rhode Island, and we are an innovator and design and engineering company, basically producing very unique equipment for testing industry. This came along, and we decided to add a few things to the original equipment, which we did. The MY05 now has a load cell, a displacement transducer, a very extensive software to evaluate its results. And I would like to discuss is on this slideshow. The unit is composed of a base and a beam, which is a balanced beam, and software. The unit has a traveling table that moves between 4 and 11 inches, 4 inches from the fulcrum to 11 inches from the fulcrum, with weights which can weigh 5 pounds each. And these weights can be up to 4. We can travel this table during the dynamic test and bring them to any point, so incrementally changing the moment of inertia of the equipment. As we change the moment of inertia of this equipment in dynamic testing, by the way, I should probably mention that the dynamic testing in compression mode and or shear mode are the two characteristic testing modes. The dynamic testing, and then we also do a hysteresis testing, and finally creep testing and a compression set test. So all these can be done on this equipment within short period of time. Dynamic testing can be between 3 and 5 seconds. Within 5 seconds, it depends on how elastic and how plastic the sample is. In other words, if the sample has high delta or loss angle, that can take a little longer, maybe 5-6 seconds. If it is an elastic product, within 3 seconds, 2 seconds, we obtain the natural frequency and all the parameters of that particular sample. So that being the case, as we can take a look on the lower left corner, the compression specimen, and the right corner, lower right corner, there is a shear specimen. So basically, this is how we move. Now, the next slide shows us the output that we generate from a test. The first thing I would like to refer to is the load versus displacement plot up on the right top corner. This specimen gives us quite an angle, quite an area under the plot, which shows that loss energy is substantial. As we go down to Jersey resilience, in this case, 16% definitely shows that it is not an elastic product, but more of a damping characteristics. The Jersey hysteresis is 83%. That is quite high, so loss energy is very high. As of course we move down to point modulus and dynamic modulus, and then of course the natural frequency 6.5%, 6.5 hertz, and that is a characteristic showing us its high natural frequency. Our natural frequency range goes from 0 to 20. We cannot go beyond that. And next is at that moment of inertia, which is calculated based on the beam moment of inertia, added on the weights and their moments of inertia to it. Then we go down to energy absorbed and power absorbed, and energy return and power return. There's a 10-to-1 ratio, as you can see. There's a lot of energy being absorbed because it's a damping characteristics, high damping characteristics. Next, we look down at loss energy tangent delta, which is 0.565, referring to a loss angle delta calculated on the basis of ASTM D5992. By the way, I would like to refer to D5992 characterizes dynamic testing systems under free oscillation and forced oscillation. Our system is a free oscillation system. The forced oscillation system is based on hydraulic, piezoelectric, or other actuators, which really can scan all the way up to a given hertz. And then it has to calculate natural frequency throughout that scan. In our case, our natural frequency comes out in 3 to 5 seconds, and that's what we are looking at. So with this 5992 test method, we do calculate the loss factor tangent delta and the angle delta. But on the other hand, we do log decrement, and we also measure phase angle. That's the difference between the two plots we have down below, which is the load and displacement against time. And that's 25 degrees, substantial. Now, tangent of phase angle is also given. Next, we go down to moment arm, which is a factor, of course. The measured force, which comes out of load cell. Final deflection, 52%. Dynamic point modulus ratio is also useful. Damping coefficient is. We also calculate E prime storage modulus, E double prime loss modulus, and E asterisk, which is the complex modulus out of those. This is for compression. We also report G prime, G double prime, and G asterisk for shear tests. Then we go to the next test, which is, sorry, okay, finally. Okay, this is called static hysteresis test, which really is, as we go back to the table, the moving table, we can initiate that motion, say, between 0.1 inch and 1 inch increments, meaning the table moves and stops for a second or 5 seconds or whatever you choose. And then it takes a measurement. It carries on, moves another increment, the same increment, and takes another measurement. And that's more of a static testing. As it does that, it can do as many cycles as you want. Now, if we look at this plot, in this case, we have 3 cycles. The first cycle, and the second, and then the third. That's what we call is Mullins effect measurement. And in our report, as you can see below, at 20.7%, we do take a measurement of static modulus on the loading side, which is 4.882, and loading side is this side, and the unloading is along this line here. We do also report unloading static modulus at 9.24, almost twice. And energy loss per unit volume is also reported. Then we also report elastic region modulus. And below, we do refer to change in strain values at maximum strain, which we think is very important for compounding engineers and technicians to know a little bit about Mullins effect. So that being the case, we go to this plot, which is a multi-plot function. In this case, we have 4 different shore values, 40 to 70, and each one has different slope, as we reported The red, which is more elastic than the others, has a slope of 1.125 megapascals. So then comes green, which is 2.707 at 50 shore A. Then comes blue, 3.5, and black at 4.8. These are different slopes. Actually, the slopes are taken in the linear region, meaning right about here. And these are the linear. And we relate this to cross-link density relatively measured. That's what we think is very important to be able to figure out. Not an absolute measurement, but a relative measurement. We go to the next slide. Here we have, as you can see, a loading curve in compression and showing an absorbed energy at loading. And then released energy at unloading. And hysteresis is the difference, of course. And as the material is more elastic, that difference is much less. If it is more plastic or more damping, the difference is quite high. Last but not least, creep test. We also do that. And it is important to be able to measure creep for various end-use applications, such as O-rings, seals. And for example, if you think of seals and O-rings, certain applications such as sealing nuclear waste encapsulated in tanks or whatever with an O-ring, you don't want that to leak if there's an earthquake or something. Meaning, if there's a danger of leak, the O-ring has to recover within its capability as soon as possible, so the leak will be minimized. And there is the natural frequency characteristics and the dynamic properties come along very importantly. Of course, seismic construction, bridge, buildings, seismic waves can be low frequency waves and are very important to protect the buildings and construction. Isolation of machinery from ground noise is very important, especially if the machinery is highly precise and highly sensitive to such noise. And also, isolating ground from heavy machinery is as important. And that basically is our equipment. We'll be very happy to answer your questions or send you more information if you would like to. And I would like to show you a video at this point. If you would like to, please stay with us. I also would like to thank again for Technobiz for giving us this opportunity, and also the CEO, Param Rao, for giving us this opportunity. Thank you very much. Then we will start running a dynamic test, dynamic in compression. At this point, we shall go to the laptop and set our initialization. We initialize and set 0. Okay, it's set 0. Now we initialize, which is 4 inches from the fulcrum. And then we go back and fill in the dynamic test data. Hysteresis.
No, this is dynamic.
Okay. Okay, and the plot appears. There are 2 of them. One shows the load versus displacement against time, and the other one, the earlier one, shows load versus displacement. Then we have a tabulation of outputs, and this tabulation is where the data is critical. Just for example, we would like to point out the Yearsley resilience and its group underneath, which is common in D945-22, the latest version of the test method of ASTM. And then underneath, there's another group of energy by integration of load cell, and the next one is loss factor and loss angle. The measured calculated loss angle in delta of 27 degrees and measured phase angle of 19.7 directly measured. Then we see moment arm, and then the complex modulus 641 psi. We have this output which we can use for dynamic tests, and then we can have a hysteresis test, which will be a test of static measurements. In a hysteresis test, onu kilitlemedin. Nuri. Boşta o.
It's okay, that's okay.
Okay. Okay. Okay, we have the data input which says minimum, the maximum moment arm 10 inches, the maximum strain 40%, maximum load 120 pound forces, pause at every step of 5 seconds, sample near between 0.1 and 1 inches, in this case quarter inch. Okay, at this point we change to 2 seconds, stop, and the hysteresis repeat is 2. The weights are 2 and each weighing 5 pounds. Once we do that, we go back to the table and start the test. As we initialize, the test starts. Moving table moves with weights on it and stops at every stop. Half inch. When it hits the limit of 10 inches or 40% or 120 pound force strain, it reverses. What's important in hysteresis is loss of energy. As the specimen experiences compression forces, when the forces are reversed, some of the energy is wasted in viscous component, and the elastic component, of course, stays the same. However, it depends on the filler structure, the agglomerate, mixing, cross-linking structure of the final component, and how it behaves once it comes out of a mold. It is also important to know about this behavior as something called Mullin's effect, meaning if the component keeps experiencing repeated stresses, it softens up. How does it soften up? It softens up because agglomerates start breaking up, forming smaller agglomerates, and therefore voids are lost, so it becomes more dense. And but on the other hand, the cross-link structure, double bonds of carbon-carbon bonds are breaking up. As they do, the material softens up. So it's a matter of how this product has to live its life, and the engineers, the technicians of rubber compounding companies should know better how to formulate and vulcanize their products at what temperatures and what conditions. This is basically what we have as we go forward in these two tests. These are the compression tests. However, we also have the shear tests. The shear specimen is composed of 2 rubber components bonded to 3 steel platens, and the forces are perpendicular to the beam. So in this case we have a shear specimen which we will run a dynamic test on, and as we can see there are 2 weights on the traveling table, and that is ready to run now. The first plot is our load versus displacement plot, and it's very clear. And then the next one is against time, load displacement against time. Tabulation is on the right, and we see outputs from there as we did before. We shall run a creep test on this shear specimen, and same conditions as we did on the dynamic test, and we will allow 60 seconds for the creep test, and we are setting up, ready to go, and go. And once the creep starts, plot collapses towards left, and displacement shows that if the creep is actually happening, which we can see a little bit here, as you can see, as the seconds move, the bar graph at the bottom shows the time function. Creep is very important for products that go into constant strain, constant stress situation under weight, such as heavy loads, seals, and anything that seals a product from ambient conditions has to be designed for good creep properties. At this point, we have to measure the compression set and include that in this calculation. And the dial here gives us the compression set measurements. Okay, thank you.
Okay, thank you, Dr. Ismail. Would you like to add any final remarks on your presentation?
Thank you, Param. We appreciate your inclusion of us in this very fine webinar. We thank you for that. We also thank the audience for their attention. We're ready to answer questions. We're ready to run tests on some samples if anyone chooses to send us samples, basically as per D945-22 specs. Other than that, we thank you again, and we hope to be at another one of these webinar sessions in the future. Thank you, Pero.
Thank you, Dr. Ismail. Let's invite the discussion session, all the speakers, please come on board. I also invite Dr. Samar Bandyopadhyaya. He will be the moderating this discussion session, and so please, every speaker, please come on board, open your webcams. Dr. Samar. Okay. Just give you Dr. background about Dr. Samar. Many of you may know him already. Dr. Samar has been with the rubber and tire industry for last close to 30 years now. Dr. Samar, yeah?
31 years.
31 years, okay. And he was involved in the tire testing, compounding, product development, and currently is as a business head of the co-project additives involved with the rubber processing additives. So, Dr. Samar, it's over to you. You have listened to all the presentations. I'm expecting that you bring the interesting discussion points among with all the speakers. Just some ground rule for all the participants, all the speakers, is that you can ask questions each to each other. Okay, you can also add any additional points if somebody gives some answer and you want to add some points. Keep it as it is not exactly Q&A. It is basically a discussion session on issues about the rubber testing. Yeah. So let's have a lively discussion among each other about the presentations and also the important issues about the rubber testing. Over to Dr. Samar. Would like to start with your...
First of all, thanks, Peram, for giving me the opportunity to speak with this gentleman whom I know very well, except I was not knowing Dr. Ismail. Otherwise, Ralph is well known to me, Dilip Dhupia, Dr. Raj Ganesh, and Andreas Mirandola as well, because his instruments, this high-tech Luxembourg 2-3 equipments we have already used in the past. So my experience, I'm sharing with you. I was in tire industry for 24 years. And 1.5 years, I was in Pidilite industry, which is making the polychloroprene rubber. And last 6 years, I'm with one additive manufacturer, like Structol or Performance Additives, this type of products. So we are selling to the tire and mechanical rubber goods industries. So first, I'm very much thankful to Dr. Ismail because he has started his lecture by naming two gentlemen, Dr. Alan Gent and Dr. Maurice Morton. You believe me, sir, when we started our rubber technology career, Dr. Maurice Morton book on rubber technology we were referring. And we studied that book on rubber technology by Maurice Morton. And Alan Gent, some of the chapters we have read from his writing. So you worked with them, and I'm really very much thankful to you. And my question to you, how do you correlate this Yardley oscillograph and the new generation, this DMA equipment? Means how Yardley oscillograph and DMA results, they will be means compared to the industry, if you can throw some light.
Thank you. Thank you, Dr. Samar. First of all, we did have a correlation done by a company in UK of DMA versus AYO4 at that time. DMYO5 was not in the works. But that came out very convincing that we had results within the frequency range we can operate. And I can provide you with that information eventually. Right now, I cannot pull that out. I'm not ready for it. But I'll be very happy to provide you, anybody interested, with that information. Actually, it's a publication we have. And that publication, I think, covers part of it. But I would like to be more specific to give you that idea. Now, it is important to understand that Yearsley oscillograph, as it was designed and built originally by Dr. Felix Yearsley, is a very rugged equipment, very simplistic, but also results are very basic. So that being the case, what we have done is we have improved its user end in today's digitized world, you know, we use the software design, all that. It came out to be a very rugged equipment to be able to use in the production environment, not just a clean environment, not just a lab environment, you know, next to a Banbury, next to a mill, or someplace where the compounders would like to be able to run some tests and then go back and change their formulations if they do so, or their vulcanization conditions. That's where we started from that angle. And what we found out, there's a basic user and a wide spectrum of users left over from the original Yearsley equipment. And they have decided to go and make the purchases from us for this new version because we have given them a wider selection with a very cost effective pricing. That's why we decided to go that route. I don't know if I was able to answer the question you presented.
Yeah.
But
it is very nice.
one more thing I want to add. Dr. Alan Gent was my dissertation professor. Dr. Morris Morton was not, but he was the director, and I bought his book and he signed it for me. So he was a great people, two wonderful individuals.
Thank you very much, sir. Thank you.
Thank you.
Yeah, and Ralph and Dilip both talked on RPA, and so my question to Dilip, you are representing Alpha Technologies and Ralph is from Montech. So both are good friends to each other, I hope.
Yes.
And so Dilip, I'm just requesting you, some of your customers from the neighboring country like Sri Lanka, they have taken this RPA, but they are using simply as like MDR. They are not able to utilize the whole potential of this excellent equipment. They are not at all knowing how to run the equipment, how to do the things properly. So can you give some light to some, maybe they are listening today, this presentation.
Okay. We can no problem in giving the training.
Dilip, your voice is not clear.
Can you increase your voice?
Whether my voice is okay?
Yeah, now okay.
Okay. So no problem at all in giving the training on Alpha instruments. Okay. So just please send me an email so that I can organize a virtual training on RP applications to the customer in Sri Lanka specifically. As say mentioned by Dr. Samar Bandyopadhyay, it will be my pleasure to give virtual training to them, and if any point of time I am there, I would like to visit the site for hands-on experience of the customer.
Thanks, Dilip. Thanks. And,
Dr.
Ralph,
Samar, yeah. But Dr. Samar,
yeah.
there are some questions for the Ralph. So let me ask Ralph. Yep. Is it all right? Yeah. Ralph, this is for you. How do you see the low temperature testing in the RPA in comparison to other techniques such as a TGA or DSC? Can it replace such kind of tests?
Frankly speaking, it depends on the polymer. Right now, the limitation for us is -40 degrees. So we can reach glass transition temperature for some of the polymer grades, but not all of them. So if really glass transition temperature need to be measured, then there are still limitations with the RPA. However, let's say for routine compound quality control, it can't fully replace, but it can complement these methods and take a lot of testing load away, especially for quality control. Yeah. So I'd say partially it may replace traditional testing methods.
Okay. Now there is another question: is that how do you cope with the material shrinkage while changing temperature?
Yeah, we have a unique direct drive system, so we can modulate the die gap. Not only we can rotate the drive, but we can also move it up and down, and therefore control the sample to have a constant normal force and avoid any kind of shrinkage. So it's a built-in system in the motor and drive system.
There is one more question here, is that what is the lowest temperature that can be reached in the RPA?
Well, at the moment, minus 40 degrees. We are working to even go lower than that, but right now the technical limitation at the moment is minus 40 degrees.
There is one more here. Which processing methods can be simulated by high shear testing? Can such systems also be retrofitted to existing machines installed in the field?
Yeah, to existing Montague rubber process analyzers, it's possible to retrofit the system. It's about a 1 to 2 day field engineer visit that is required. What methods? Basically, any kind of high shear processing. It starts from mixing, milling, calendering, but most customers are actually interested right now in extrusion, especially from the tire industry, tread extrusion, tread performance, but also for the technical rubber industry, injection molding. We have quite a good number of customers using the system for this application.
Okay, thanks, Ralph. Over to you, Dr. Samar. Any further points to add?
Ralph, would you elaborate regarding, you told that raw polymer, green compound, cured rubber, everything can be tested through the RPA, and it is a fantastic machine regarding to all these studies. Can you a little bit elaborate?
Well, there are different international standards, of course, for all these kind of segments. ASTM 6204 to classify and characterize different polymers, ASTM 6601 for processing. There is a standard for pain effect and a lot of standards as well for after cure dynamic properties. However, what most customers are nowadays doing, and what I am working on with our customers, is to actually replicate their process conditions. So we look at their, for example, raw materials they are purchasing. Is it a natural rubber? How do they process it? How do they masticate the material? And then try to replicate these exactly in the RPA. This means shear rate and temperature. So it does not really matter if it's already a compound, if it's still a raw polymer, due to the highly extended capabilities, thermal capabilities, but also shear rate capabilities. Almost any kind of production relevant condition, or also later on process or application specific condition, can be covered. But to really get applicable data with the RPA, it's always a process. So yes, of course you can run tests according to standards. However, the result and knowledge you can gain from that will be very limited. So we're very closely working with our clients to understand what their materials are facing through their different production steps and life cycles, and then set up the RPA accordingly. There are millions of different combination possibilities of RPA programs, and therefore it's really taking the customer on the hand and guiding them through this, and then finding correlations. And this is a process. It's not a simple process. It's not just doing installation, but with most of our customers, we have a very, very strong and deep relation and continuously supporting them. But there is not like one general recipe that please do this and you will get all the information, because all the different processing steps in the rubber industry are so different. Of course, tire industry, there are more similarities, but when you go to the technical rubber industry or even raw materials, the manufacturing processes are so different, and therefore the approach to different testing sequences and processes is also really different.
Okay, Dr. Samar, there is a question for Andrea. Let me address it. Okay, Andrea, this is for you. When we speak about structural properties, what is the difference between OAN and void volume?
Both are related to the structure of carbon black. Is a different way to measure. let's say that the OEN has a history that is much longer because it was the test method was developed, I think, in the early 60s or late 50s. So it's a method that where the producer of carbon black, they have tons of data to compare and to analyze. So it's the downside of the method is that in some countries they still use the DBP oil, which is a hazardous material. And each test is producing between I don't know 50 and 100 grams of waste, and OEN test takes between 20 and 30 minutes, and the COEN test even more because you have also to compress the material 4 times and to prepare the sample. Void volume is a relatively new test method. It has been introduced in the D1765, so that the parameters to characterize carbon black for rubber application only 1 or 2 years ago. There are not that much data to compare. It's still a R&D method. On the other side, is really fast because it testing on material is a few minutes maximum, and you use between 1 and 4 grams of material without any oil, without any pollution. So it's a different test method. I would say probably is the future. I mean, it's giving you much more data that need to be compared, need to be correlated, need to be studied, but is a much more complete equipment compared to the OEN machine.
There is one more question for you, Andrea. Is the pellet hardness tester suitable for other materials other than carbon black and recovered carbon black?
It can be. I mean, it depends on the hardness of the pellet and on the size and form of the pellet. Our pellet hardness tester has been engineered for a pellet that have a spherical or a round form, like a potato or something like that, you know. And if you use material that are, you have pelletizers that are producing flakes instead of small sphere, we have problems to measure. We have a good experience with zinc oxide, for example. We have some customers, we did some tests, some benchmarking, so we good results and satisfactory for our customer. With other material, we don't have that much experience, but there is a possibility to test or to evaluate also other materials. The second limitation could be the hardness of the pellet, because our pellet hardness is going up to around 200 centinewton. I don't think that in rubber compounding you have a material pelleted that has a hardness more than 200 centinewton. It's probably on the range of 50, I would say. You will correct me if I'm wrong, but it's on the range of 50, 30, something like that. Otherwise, you have too hard pellets and you generate bad dispersion.
Over to you, Dr. Samar.
Yeah, Andreas, I have a question for you. Like I have seen the pellet hardness, particularly the compression pellet hardness. People are using the compression machine locally made, and then they go for the pellet strength checking through your machine. Do you advise these locally fabricated machines for compressing the pellets is suitable?
Well, it's like if I'm advising my competitor, I'm not aware about this compression machine. I mean, I know that there is something in Japan that is produced, but they have a different market from compared to us, let's say that, and another equipment. But locally produced, I'm not aware about this kind of equipment. I know that there is a manual pellet hardness where you crash pellet by pellet manually. Well, it's time consuming because with our machine, you put a spoon of sieved material and you let the machine run, and you have a repeatability of the result. You have a recording and so on. when you do a manual pellet hardness, breaking each pellet one after the other, is really depending on the operator. You have to put everything on the paper. Well, it's a different test, and of course, is not according to the ASTM standard test method. So there is no other test method now than the D5230, that is automated pellet hardness testing, because the manual has been withdrawn without replacement already 3-4 years ago, I think. So there is no more manual pellet hardness testing considered by ASTM. This doesn't mean that a producer or a user can test on his own with his own proper internal test method. It means that officially, if you want to speak the same language between a user and producer, you cannot use this test method. The results are not taken in account if you want to, I don't know, complain about a batch of material you received or something like that, because nobody will give you credibility if you tested manually your sample.
Thank you. Thank you.
You're welcome.
For Samar, we have a couple of questions for Dilip. Dilip, is Sub-Zero technology is only for tire industry only? Your comment, please.
At present, we targeted the tire industry, but the technology is very much useful for the other non-tire products, say for example, seal application or for some belt application. And it will be very helpful for the conveyor belt industry also.
Okay. Rock, do you want to add anything relevant?
So basically, I agree. We have our low temperature system now since 4 years in the market, having sold about 500 of these. And I would say the minority is tire industry of it.
Okay.
Most of it goes to raw polymer testing, goes to technical rubber industry.
And Dilip, there is another question here that RPA, how it will improve FTQ?
Yeah, say for example, RPA is very much helpful in the quality control for the incoming raw rubber for the rubber industry, in terms of generating the qualitative data based on the molecular weight as well as the molecular weight distribution, and followed by some test combination like the dispersion, then your processability test to ascertain the processability. If any industry, they are able to prepare specification for their raw polymer or for the mixed rubber compound, or if they are able to optimize the mixing process based on the data generated with the help of RPA, then it will be very helpful for them to achieve a FTQ in terms of using the correct raw polymer which is suitable for their mixing equipment, and optimizing the mixing cycle for every batch to get the maximum output from the minimum resources input, such that all the down the line processing is very good for the optimized rubber compound, and it will reduce the rework on rubber compound. Thus, FTQ is being attained with the help of RPA. Thank you.
Dilip, Dr. Samar, over to you.
Yeah, so we must thank each of the speakers. We are missing Dr. Raj Ganesh.
Okay, Dr. Samar, when I ask Dr. Ismail a couple of questions. Dr. Ismail, first of all, you know, I mispronounced it. It's a DMYO5. That's why I call DYMOV. Okay, my apologies on that. I'm apologies on that. Okay.
That's
The second issue is that, if somebody wants to purchase your equipment, do you guys have a representative in Asia, or what it is like?
Yes, we're in the process of developing our network. And it's not really complete yet, but we'll be happy to work with the end users directly at the moment with a service availability going forward as we go by. So we'll be very happy to evaluate any applications as per country basis or regional basis, meaning representing us in that region, giving us the service capability. We are not a big company, we are small. We are on an innovation, engineering, design end of it, but we have proven we've already sold our equipment and to very substantial companies. So it is very important to be able to support that. Therefore, we do support remotely, of course, and also the equipment is plug and play. In other words, when we shipped to a country, I'm not going to mention which country, but there was a problem of traveling at that time, we were able to support them so they could start. We did training remotely. We did start up without being there at all. So it's a very easy process and very user-friendly, by the way. So I don't think we would need anything that deep as far as installation and training to be there for 3-man days or 4-man days or whatever, and charge the customer for that also. That's another issue. But we'll be happy to work with anybody who is interested. Please have them contact us.
Yeah, I'll keep you posted. I think we can share the information about your equipment, and also not only you, all other speakers. Okay, so we can extend our support. As you know, Technoviz is specialized in hosting a lot of events. I'm happy to support. I think you may know this IRC is going to happen in Bangalore. Okay, maybe that is one place that if you're looking for meeting Indian or even overseas, rubber industry people, tire industry people, it's going to happen IRC during the 24th to 26th November in Bangalore. Dr. Samar is the technical program convener. So if you're interested to make a presentations, I think there's opportunities also there. Is it right, Dr. Samar? Would you like to add anything to it? I don't want to do your promotion.
Actually, I want to
show him. I want to show him the book.
Same book. So IRC right now we are oversubscribed as far as the technical papers are concerned. But still, if we get some foreign speaker, it is welcome, because IRC around 65% contribution should be from the foreign speakers. So Indian, we have shut the door already for our country people, but still we can take some papers from abroad.
Okay. Thank you, Dr. Samar. Guys, in actually this session I'm expected is going to be long. It is a long one today. As you know, this is it's recorded, and each presentation will be separated and promoted again to share it to all the subscribers of the Rubber Industry NewsHour. Before I end this program, I'd like to request you to give a final remarks to the audience. May I go with Ralph first? Yeah.
Thank you very much for the opportunity. Of course, I'm looking forward to see you all in person, hopefully at the IRC in Bangalore later this year. And once again, thanks very much for the opportunity. And yeah, looking forward to be in touch. And like I said, hopefully see you in person at some point.
Thanks, Ralph. Andrea, over to you.
Thanks a lot. It was a great opportunities and really interesting topics. In my presentation, there were all my contacts. In case you have any further question or commercial contacts, technical question, we are here. So just get in contact with us.
Okay, thanks, Andrea. And Dilip.
Thank you, Madam, to organize the webinar on advancement in the testing technology. I think this is the first of its own kind in the rubber industry network, because usually people, they wish to listen about only about the rubber compounding, rubber testing, rubber processing, but they're being the least interest in the what are the advancement of over there. And really, it is my pleasure to present the latest launch from Alpha Technologies, and I will be it's more than happy to help if you have any say technical queries or any other help in equipment selection. I'll be more than happy to help, and I have just mentioned my email ID on the last of my presentation. Once again, thank you very much, Param. Thank you very much. Yeah.
Thanks, Eric. May I ask Dr. Ismail?
Thank you, Param. Thank you, Dr. Samar. I'm really honored to meet and to be in this group of people, professionals, and to be outside of US and worldwide. I would like to say that we will not be able to attend the particular fair, trade fair. However, we'll be at your service anytime, yours as well as end users. With any questions, I'll be happy to answer. Any tests you would like us to run just for some information, we'll be happy to do that as well on our equipment. And again, be safe. Hope to see you again some other time.
Thank you, Dr. Ismail. May I ask Dr. Samar? Thank you very much for moderating and joining me to bring some issues to discuss with these equipment. We call it suppliers. At the same time, they're also well experienced in developing the instrumentation for the benefit of the rubber industry. Yeah, Dr. Samar, any final remarks?
Yeah. Param, you are doing a great job, because this is a refreshment for all of us as well. When a speaker is saying something, we know something, but when he is repeating, it is a recapitulation of our knowledge, existing knowledge. So we must thank each of them. Every one of them given the background information at the beginning, and then they gone for the advancements. So it's a big learning for all of us. Thanks to each of the speakers. And also many thanks for Param for organizing this type of event.
Okay, guys, thank you very much. Thank you all of you once again for being part of this advances in rubber testing instrumentation. This is going to be a series, this is basically part one, because there are many other instrument suppliers also want to be part of it, but we cannot accommodate all at one place. So there will be, kind of a part one, part two type of, the segments of the advances in rubber testing instrumentation. Thank you all for being part of this part one officially. Okay, and I look forward to seeing the future, program. Yeah, guys, that's the end of this episode today of the Rubber Industry NewsHour, the episode number 33. Which will focus on the advances in rubber testing instrumentation. And if you like to watch this full session, you can always go to our technology channel on YouTube. There will be, each presentation will be divided and also uploaded separately, and you're free to check it out whenever it is convenient to you. We will be sending all the subscribers a link reminder to watch this session whenever it is convenient to you. Thank you all. I see you again next episode. Sorika. Thank you very much.
Bye-bye.
Thank you. Bye. Bye.
Bye-bye.
Thanks, everyone. Talk to you again soon.
Bye-bye.
Cheers.
Cheers.